Welcome. In this video I'm going to go through Unit 1 worksheet packet. We have gone through some of these problems in class already, but I'm going to show you how to do each one and explain why the answer is the way that it is in the key. So let's begin with number 1. Identify the following as chemical or physical changes. Remember that a chemical change is when the identity of the substance changes, and a physical change is when the identity of the substance does not change. So let's go through each one. First is compressing hydrogen gas into a liquid. Now, going from a gas to a liquid is a phase change, meaning that it changes from liquid to gas or from solid to liquid or vice versa. And so compressing hydrogen gas into a liquid is a physical change because the hydrogen gas is still hydrogen. It's just a liquid. Next is frying an egg. Frying an egg is cooking. And most cooking is chemical changes because we are applying heat to some substance. Usually it's food. And we want to make it more palatable. We want to make it safe to eat. So frying an egg is certainly a chemical change. Although the egg also undergoes a phase change, it changes from a liquid to a solid, it undergoes a chemical change. It changes color, changes texture, it changes in flavor mainly. And so most cases where cooking takes place, those are chemical changes. Burning gasoline in your car. Burning anything is a chemical change. We're taking gasoline and we are burning it into carbon dioxide and water through the process of combustion. Turning whole milk into skim milk. Now, whole milk is simply milk that is in its essentially it's in its raw form as it came out of the cow. It's been pasteurized, of course, but it has not been altered in any way. Skim milk means that the cream from the whole milk has been skimmed off. So cream is composed of a lot of the fatty molecules in milk, and those have been skimmed off. So the only thing that's taken place here is that the fat has been removed from the whole milk, and it's a physical alteration. It's not a chemical one. And so that is a physical change. Tearing a piece of paper, that's a physical change. The paper is the same substance, it's just now in two pieces. Cracking the screen of your phone is a physical change. Again, the substance hasn't altered in any way, it's just now in more pieces than it was to begin with. Rust forming on a nail. Rust is a great example of a chemical change. A nail is a silvery color, and when rust forms on it, it changes color. And the reason why it changes color is because it actually changes its chemical properties. It's an entirely different substance after rust has formed. Rust is iron oxide, whereas the original nail was just simply iron. So I can draw this out here. Iron plus oxygen forms iron oxide, and this is rust. And I know this is not balanced, but just showing you here for illustrative purposes what is happening. So this is a chemical change. H is my favorite, an apple growing on a tree. Absolutely a chemical change. The apple tree, through its leaves, takes in all sorts of things. Sunlight, takes in air in the form of carbon dioxide, takes in nutrients from the roots in order to form an apple. And so many, many, many chemical changes have taken place so that the apple can be produced from the tree. All right, so that's number 1. Let's move on to number 2. For each pair Rank the items in terms of increasing energy, combining potential, and kinetic. So what I'm getting at with this one is I want you to think about all of the types of energy that are possible, especially with D. It's not really so much important with A, B, or C, but with D it will be. We'll talk about that when we get there. So, which has more energy, helium gas or liquid helium? We've talked about this in class. Substances in their gas phase have more energy than substances in the liquid phase. Okay, so this I would say is do helium gas, then helium liquid. If we're ranking them, in terms of, this would be in terms of decreasing energy, so let me change this here. This would be helium liquid, and then helium gas is more energetic. So as we move to the right, it's more energy. Ice or steam, this one actually is already in order. Ice is a solid form of water, and steam is the gas form of water. So moving from left to right, we are increasing energy, going from ice to steam. Steam has much more energy in it than ice does. Melted snow versus snowflakes. Snowflakes contain less energy. These are the solid form of water, and melted snow, of course, being the liquid form of water. And so melted snow is going to contain more energy. It has absorbed more energy from the ground or from the sun in order to melt. So that's the order for C. Pizza and CO2 and H2O exhaled after digestion of pizza. For this one, I want you to think about the potential energy that's in pizza. You could make the argument that, well, CO2 and water, vapor, are gases, so they must be more energetic. But when you consider the chemical potential energy, the amount of energy that could be gained from pizza by eating it through our bodies, pizza contains tremendously more amount of energy than CO2 and water. We can't breathe in CO2 and water and be able to move, for example. Our bodies need food. We need carbohydrates, proteins, fats in order to be able to function. Pizza contains all of those, and once it's broken down through the process of digestion, it will yield CO2 and water. So if we're doing this in terms of increasing energy, pizza contains much, much more energy than these two. These are actually byproducts of respiration. This is the waste that our body forms after digesting pizza. Okay. Number 3. Draw a heating curve for water and indicate the appropriate temperatures for phase changes. So that's A. Let's go ahead and do that one. Down here we have heat added on the x-axis, and up here we have temperature. It doesn't matter what the scale is. We start off with ice. Very cold. It doesn't really matter, again, where we even start. This isn't really 0. It's not important, though. Just going to draw this out and then explain each bit. Okay, so this is a heating curve. Down here we have the solid phase of water. This is ice. Here we have the melting point. Here we have the liquid phase of water. Here we have the boiling point. This could also be called the freezing point. They're the same temperature, just different names. And then up here we have the gas form of water, which is steam. Liquid, we just call that water. Okay, so here's how this thing works. As heat is added, the temperature goes up, right? We know this. You can stick a pot of water on a stove, turn it on, and heat is being added to that pot, which in turn is transferring heat to the liquid water. And we know that that water will eventually get hot and boil. That would be this right here. Okay, that would be that particular line. Down here, we know that if you take ice out of the freezer, eventually it's going to melt. And the energy that comes from melting, or that is provided to the ice in order for it to melt, comes from the air. Hopefully, the air that you're living in is not as cold as your freezer is, so when you take it out, heat will be absorbed by the ice and the temperature will go up. Most freezers keep the ice at about -20 degrees Celsius, so that temperature has to come up 20 degrees in order for it to melt. Once it's melted, it becomes liquid water and then, of course, continues to absorb heat from the air and heats up to room temperature, unless you put it in a pot and boil it, at which point it will boil. Now, here's the deal. This is at 100 degrees C. Melting point is at 0 degrees C. Notice how these are flat lines. That means that they do not change in temperature. We can continue adding heat, but the temperature doesn't go up. These flat lines are known as the heat of vaporization on this one. So this is heat of vaporization, and this one over here, heat of fusion. We're not going to get too much into these two terms. Just suffice it to say, at these points, at 0 and at 100, the temperature doesn't change until either at 0 all of the ice is melted, or at 100 all of the water has boiled off. Okay, we won't even get into talking about this because you really don't experience this in your everyday lives. Really, your experience with water is going to be from about -20 degrees C down here up to boiling. So I think I described all the physical processes when ice is converted into steam. Now let's talk about endothermic versus exothermic. If we are moving up the curve, that means from left to right, all of those processes are endothermic. That means they require heat to be absorbed by the water. So the process of melting is endothermic. The process of boiling is endothermic, and everything in between going from left to right. If the temperature is increasing, it's endothermic, or if it's melting, or if it's boiling. Remember, those temperatures aren't changing. Now, if we go the reverse direction from right to left, we call that condensation. When we move from steam back to liquid water, we call that condensation. Okay? And if it's condensing, that's exothermic. You can test this. I don't recommend it, but if you really want to, you can test this by sticking your hand over a boiling pot of water. What you'll notice is your hand gets very hot. And it's not because you're sticking your hand over something hot. It's because the water is condensing on your hand and it's releasing a lot of energy. We call that exothermic. Similarly, coming down here, ice freezing, or water freezing into ice. So that's, again, going from right to left. Water freezing into ice is exothermic. It's releasing energy. So if we're moving from left to right, endothermic, from right to left, those processes are exothermic. All right, moving on to number 4. We have temperature conversions. Now you need to memorize the conversion formula from Celsius to Fahrenheit, and vice versa. Although I recommend you just memorize one of them and then algebraically manipulate it. So here's one that I'm going to write. Degrees Fahrenheit is equal to degrees Celsius times 9/5 plus 32. Okay, and if we algebraically manipulate that to get the other one, we then find that degrees Fahrenheit minus 32 times 5/9 is equal to degrees C. Okay, so you can memorize both, or you can just memorize one and manipulate to get to the other one. All right, so the first question, 58 degrees C into Fahrenheit. So I'm going to use this formula here. 58 times 9/5 plus 32. Now I'm going to show you how I would input this on a calculator. Ooh, let me see if I can get rid of that glare. So 58 times 9/5. It's okay to do that. I'm going to go ahead and hit enter, add 32, and I get 136.4. And that is degrees F. Now we're going the other way with this one, 98.6 degrees F minus 32 times 5/9. Again, I'm going to show you how I'd input that. So 98.6 minus 32, and then multiply by 5 divided by 9, and end up with 37. And that's degrees C. Then 103 degrees C times 9/5 plus 32. Not going to do the calculator with that one. That's 217.4 degrees Fahrenheit. Okay, this video is long enough, so I'm going to actually divide this into 2 videos. So we're going to stop right here and pick up with the other one in part 2.